On the night of July 1st, 2025, a telescope in the Atacama Desert of Chile was doing what it does every single night. It was sweeping the sky, methodically, frame by frame, looking for anything that moved. The telescope belongs to a network called ATLAS, the Asteroid Terrestrial Impact Last Alert System. It was built to find things heading toward Earth, rocks, comets, objects that could cause damage. It scans the entire accessible sky every 2 nights, hunting for faint points of light that shift position from one image to the next. That night, in a part of the sky so crowded with background stars it was nearly impossible to resolve individual objects, a region near the dense star fields of the galactic plane, close to the centre of the Milky Way itself, the telescope caught something. A faint smudge, moving at 1/2 degree per day across the sky, fast, moving wrong, moving in a way that nothing gravitationally bound to our sun should move. It was given a temporary designation, a 11PL3Z. Placeholder letters and numbers, the way all new objects are labelled before anyone knows what they actually are. Within 24 hours, astronomers around the world had pointed their own instruments at it. The Zwicky Transient Facility in California found pre-discovery observations going back weeks. The Lowell Discovery Telescope in Arizona confirmed it. The Canada-France-Hawaii Telescope on Mauna Kea confirmed it. Observers in Chile and the Canary Islands confirmed it. And what they confirmed was something remarkable. The orbital path of A11PL3Z could not be made to fit a closed loop. It didn't travel in an ellipse, the way every planet, every moon, every comet and asteroid that belongs to our solar system does. Its trajectory was hyperbolic. It was moving far too fast to be held by the sun's gravity. It was passing through, not visiting from the outer edges of our own system, passing through from somewhere else entirely. On July 2nd, 2025, the International Astronomical Union's Minor Planet Center made it official. The object was given a permanent name, 3I/Atlas. The 3 stands for the third. The I stands for interstellar. It was only the third object in the recorded history of astronomy confirmed to have travelled to our solar system from another star system entirely. The first had been 1I/Oumuamua, discovered in 2017, shaped like nothing anyone had seen, possibly elongated like a cigar, possibly flat like a pancake. It had moved through the inner solar system and left before we could study it properly, and it had done something with its trajectory that no one has fully explained to this day. The second had been 2I/Borisov, found in 2019, a more conventional visitor, a comet with a recognisable tail, shedding gas and dust the way comets do. It gave scientists their first real chemical window into the material of another solar system. And now there was a third. 3I/Atlas was moving at 58 kilometers per second relative to the Sun, the highest hyperbolic excess velocity ever recorded for any object passing through our solar system. That speed, combined with the shape of its orbit, tells astronomers something important. That speed had not been gained by falling toward our Sun from the outer fringes of the solar system. It had been acquired over a vast stretch of time and space, through gravitational interactions with countless stars, and nebulae encountered during a journey measured not in years or centuries, but in billions of years. This object had been drifting through the dark between the stars longer than the Earth has existed, and now it was here, moving through our neighbourhood at a speed no human spacecraft has ever achieved, heading for the inner solar system, shedding material as the sun's heat finally reached it for the first time in its incomprehensibly long journey. Within hours of its official naming, every major space telescope on the planet had a new target. Hubble, the James Webb Space Telescope, the Gemini observatories, the ESA missions already stationed across the solar system. NASA began pulling together a list of every spacecraft in the inner solar system that could be pointed at 3I/Atlas. The list was long, and over the following months, as observatories around the world collected data and astronomers began to argue about what it all meant. One thing became clear very quickly. 3I/Atlas was not going to give up its secrets easily. It was big, but nobody agreed on how big. It was a comet, but a deeply unusual one. Its chemistry violated the patterns we'd established from studying hundreds of comets in our own solar system. Its trajectory raised questions that some scientists found fascinating and others found alarming. And one of the most credentialed astrophysicists on the planet looked at the whole picture, the trajectory, the timing, the chemistry, the behaviour, and asked a question out loud that made much of the scientific community uncomfortable. What if it wasn't natural? Over the next few hours we're going to walk through the complete story of 3I/Atlas, from the night it was found in those dense Chilean starfields, to the months of observation and argument that followed, to the moment it disappeared behind the sun, to its closest pass to Earth in December 2025, and forward to where it's headed now, outbound and accelerating, never to return. This is the story of a visitor from another star, of what it told us about the universe, and of the question it still hasn't fully answered, no matter how many telescopes we pointed at it. Let's begin at the beginning, not at the moment of discovery, but much, much further back than that, because to understand why 3I/Atlas matters, you first have to understand the universe it came from. The observable universe is approximately 93 billion light-years across. That number is almost impossible to hold in the mind in any meaningful way, so let's try to shrink it down. If the entire observable universe were the size of Earth, our galaxy, the Milky Way would be roughly the size of a red blood cell, something you'd need a microscope to see. Within that red blood cell there are somewhere between 100 billion and 400 billion individual stars. The most current estimates lean toward the higher end of that range, and we now know, with reasonable confidence, that most of those stars have planets. The Kepler Space Telescope spent 9 years staring at a tiny patch of sky, measuring the brightness of 150,000 stars, and found that planetary systems are the rule rather than the exception. When a star forms from a collapsing cloud of gas and dust, planets are almost inevitable. They're a natural byproduct of the same process that creates the star itself. When those planets form, they're violent. Giant planets migrate inward and outward through the protoplanetary disk, slinging smaller bodies around through gravitational interactions. Comets, asteroids, chunks of rock and ice, they get hurled outward, thrown into eccentric orbits, and eventually ejected entirely from their home systems, cast into the space between the stars. Every star system that has ever formed planets has almost certainly thrown material into interstellar space. Over the billions of years that stars have been forming and evolving and dying across the Milky Way, an enormous quantity of interstellar debris has been accumulating in the spaces between stars. Drifting, cold, dark, invisible at any individual distance, but present in aggregate numbers that stagger the imagination. We just didn't have any way to see it until recently. The Atlas Telescope Network, along with other wide-field sky surveys like the Zwicky Transient Facility and the Vera C. Rubin Observatory, represents a genuine threshold in human capability. For the first time in history, we have instruments sensitive enough and fast enough to detect small, faint, fast-moving objects at distances of hundreds of millions of miles. We've crossed a threshold, as David Jewett of UCLA, who led the Hubble observations of 3I/Atlas, put it. Objects that have been passing through our solar system since long before humans existed are finally becoming visible to us. The University of Hawaii's Institute for Astronomy estimates that there is at least one interstellar object as large as 3I/Atlas, or larger, passing through the inner solar system every 5 to 10 years. But for most of human history, for all of it, really, until about a decade ago, we had no way to find them. They would pass through, shine briefly, and vanish back into the interstellar dark without leaving a single record. Oumuamua changed that. Borisov confirmed it. And 3I/Atlas made it undeniable. Interstellar objects are real. They are passing through our solar system, and now we have the tools to study them. But 3I/Atlas was different from its predecessors in ways that went beyond simply being the third of its kind. It was faster. It was, by some estimates, more massive. It was exhibiting activity, shedding gas and dust, that suggested it was compositionally distinct from anything we'd studied in our own solar system, and its arrival had been preceded by what one group of scientists described as a set of orbital coincidences, so unlikely that they deserved, at minimum, a second look. To understand why those coincidences made people uncomfortable, we need to go back to the beginning of the story. Not the universe's beginning, but the beginning of the discovery itself. The night in Chile, when 4 30-second exposure images changed everything. The Atlas station in Rio Hurtado, in the Atacama region of Chile, is one of 4 telescope units in the Atlas network, which was funded by NASA specifically to find potentially hazardous objects before they find us. The Chilean unit, sometimes called Atlas Unit 4, was added to extend the survey's coverage into the southern hemisphere sky. On July 1st, 2025, it was sweeping through the dense star fields near the galactic center, a part of the sky that is notoriously difficult to work with because the density of background stars makes it genuinely hard to identify individual moving objects against the noise. Amateur astronomer Sam Dean later speculated that this was precisely why 3I/Atlas had not been found earlier, despite pre-discovery observations tracing back to at least May 2025. It was hiding in plain sight, lost in the crowd of stars behind it. The 4 images that triggered the discovery alert showed a faint point of light moving in a way consistent with a fast-moving nearby object. The alert was submitted to the Minor Planet Center within hours, and then the confirmation cascade began. Pre-discovery observations were found almost immediately. Zwicky transient facility images from June 28th and 29th matched the trajectory. Earlier ZTF observations from June 14th through June 21st were recovered and matched. Atlas itself had earlier observations going back to June 25th. Dean identified additional Atlas observations from as early as June 5th, 2025. Those pre-discovery images were crucial. They gave astronomers a longer baseline to work with when calculating the orbital elements, the parameters that describe an object's trajectory through space. And when those calculations were done, the answer was unambiguous. Eccentricity approximately 6.14, an orbit so hyperbolic, so decisively unbound from the Sun, that there was no alternative interpretation. This was not a comet from the Oort cloud. This was not an asteroid on a highly elliptical path. This had come from somewhere else. By the time the Minor Planet Center formally announced the discovery on July the 2nd, 2025, the object's interstellar designation was already secure. 122 observations from 31 different observatories had been incorporated into the initial orbital solution, with a mean residual of just 0.3 arcseconds. The orbit was well constrained. The conclusion was definitive. 3I/Atlas was the third confirmed interstellar object in human history. David Jewitt, who would go on to lead the Hubble Space Telescope observations of the comet, described what was happening as a threshold moment. This latest interstellar tourist is one of a previously undetected population of objects, he said, that will gradually emerge now that we have powerful sky survey capabilities that we didn't have before. He was right. But none of the previous interstellar visitors had generated the kind of scientific and public debate that 3I/Atlas was about to spark. Because unlike Oumuamua, which had been too strange to classify, and unlike Borisov, which had been reassuringly normal, 3I/Atlas seemed to be both at the same time. Normal enough to be confidently called a comet. Strange enough that a Harvard astrophysicist would look at the data and ask publicly and repeatedly whether normal was really the right word at all. Within days of the discovery announcement, the world's most powerful space telescopes were being repositioned. Time is everything with a fast-moving object. 3I/Atlas would not wait. The Hubble Space Telescope captured its first images of 3I/Atlas on July 21st, 2025, when the comet was approximately 277 million miles from Earth, roughly the distance between Earth and Jupiter. The images were taken with Hubble's Wide Field Camera 3 and processed by Joseph De Pasquale at the Space Telescope Science Institute. What Hubble revealed was both reassuring and puzzling. The reassuring part, 3I/Atlas had a coma. A coma is the glowing cloud of gas and dust that forms around the solid nucleus of a comet as it heats up in the sun's warmth, with frozen volatiles sublimating, turning directly from solid ice to gas, and carrying dust particles with them as they escape into space. The presence of a coma confirmed what the initial ground-based observations had suggested. This was an active comet, not a bare rocky asteroid. It had ice. It was reacting to the sun. The puzzling part, the shape of the coma, was unusual. Hubble showed a teardrop-shaped cocoon of dust coming off the nucleus. There was a plume on the sunward side, a jet of material being pushed toward the sun, which is the opposite of what you'd normally expect from solar radiation pressure, which should push dust away from the sun. And there were hints of a very faint, broad tail pointing away from the sun, but it was not clearly developed yet. Taken together, the images told a story of an object that was active in the way comets are active, but doing it in a slightly unfamiliar way. The asymmetric coma, the sunward plume, the teardrop structure, none of these were impossible. All of them were interesting. David Jewett, who led the Hubble observation campaign, said the images showed the comet had a teardrop-shaped cocoon of dust, and that Hubble's data was yielding a dust loss rate consistent with comets first detected around 300 million miles from the sun. That behaviour, he noted, was much like the signature of previously seen sun-bound comets originating within our solar system. The big difference was simply where it came from. The same Hubble data also provided the first serious constraints on the size of the nucleus, the solid icy heart of the comet hidden within the glowing coma. This is where things got complicated. Before Hubble weighed in, early estimates based on ground-based observations had placed the diameter of the nucleus at approximately 20 kilometers. That would have made it significantly larger than the asteroid widely believed to have struck Earth 66 million years ago and ended the Cretaceous. It would have been an enormous object by the standards of any comet. The estimate was driven by the extraordinary brightness of 3I/Atlas at the distance where it was discovered, farther out than Jupiter, where most comets are too cold and dark to develop any coma activity at all. But the early estimates were wrong, and in a sense that made the object more interesting rather than less. The Hubble data, analysed in August 2025, placed the upper limit on the nucleus diameter at 5.6 kilometers. That's roughly 3.5 miles across, smaller than a typical city but still a substantial object, and the actual nucleus could be considerably smaller than that. The lower bound from Hubble imaging was approximately 320 meters, though independent analysis using the non-gravitational acceleration of the comet's orbit suggested a nucleus diameter of between 0.52 and 0.75 kilometers, about half a mile to 3/4 of a mile, as the most physically consistent estimate. There's a reason the range is so large. The nucleus of 3I/Atlas cannot be directly seen, even by Hubble. It is surrounded by a bright coma of reflective dust that outshines the nucleus itself, like trying to photograph a candle as sitting inside a searchlight. Astronomers have to model the coma's brightness and subtract it to estimate what the nucleus must look like. The uncertainty in that subtraction produces the wide range of possible sizes. What can be said with confidence is that the nucleus is not 20 kilometers across. The early estimate was driven by the brightness of the coma, not the nucleus, and the coma of 3I/Atlas was, it turned out, unusually reflective and active for an object so far from the sun. That activity itself was one of the things that made the comet scientifically fascinating. Most comets in our solar system are frozen and inert when they're as far out as Jupiter. They don't develop their glowing coma until they get closer to the Sun, usually inside the orbit of Mars, where solar radiation becomes intense enough to start sublimating the ices on their surfaces. The fact that 3I/Atlas was already glowing, already shedding dust and gas at Jupiter's distance, implied that it was particularly rich in highly volatile compounds, substances that sublimate at much lower temperatures than water ice. The James Webb Space Telescope confirmed this suspicion when it made its first observations of 3I/Atlas in August 2025. Webb's near-infrared spectrograph analysed the light coming from the coma of 3I/Atlas and broke it down into its component wavelengths, identifying the chemical fingerprints of specific molecules. What it found was unexpected. The coma was dominated by carbon dioxide gas. Water was present. Water ice had actually been detected earlier in July by NASA's Infrared Telescope facility on Mauna Kea, and gaseous water was detected in late July by the Swift Observatory. But it was a secondary component. The ratio of carbon dioxide to water in the coma of 3I/Atlas was approximately 8:1. 8 molecules of carbon dioxide for every molecule of water. That number is extraordinary. In the comets of our own solar system, the ones we've been able to study directly, water is almost universally the dominant ice. Even comets that are carbon dioxide rich rarely exceed a ratio of 1:1 for CO2 to water. The 8:1 ratio observed in 3I/Atlas was described by scientists as one of the highest ever recorded in any comet. Webb also detected carbon monoxide, carbonyl sulfide and water ice grains in the coma. The full chemical picture that emerged was of a body whose outer layers had been substantially modified by billions of years of exposure to cosmic radiation during its journey through interstellar space. The surfaces of comets in our own solar system are also processed by radiation, but they haven't had billions of years of unshielded interstellar travel to accumulate that processing. 3I/Atlas apparently had. University of Oxford astronomer Matthew Hopkins analysed the trajectory and composition data and suggested in early reporting after the discovery that 3I/Atlas might be more than 7 billion years old, older than our solar system by more than 2.5 billion years. If that estimate is correct, 3I/Atlas formed around a star that no longer exists, a star that burned through its fuel cycle and died billions of years before our Sun ignited. It would have been travelling through the Milky Way since before Earth was a thought. Whether Hopkins's age estimate proves correct or not, the chemical data from Webb told a consistent story. This was an object from a different solar system with a different chemistry, shaped by conditions we can only partially reconstruct. The 8:1 carbon dioxide to water ratio suggested either that it formed in a very cold, carbon dioxide rich part of its home system, in a region far from its parent star where water ice would sublimate away over geological time but carbon dioxide ice would remain stable, or that its outer water-rich layers had been destroyed by the accumulated radiation of billions of years in interstellar space, leaving a CO2-dominated rind. Either way, it was chemically unlike anything we'd studied before. And then there was the colour. Spectroscopic and imaging observations from multiple telescopes showed that the coma of 3I/Atlas had a distinctly reddish colour. The spectral slope was measured at approximately 22.8% per micrometer in the optical range, which is a measure of how much redder the object looks at longer wavelengths compared to shorter ones. That value places 3I/Atlas firmly in the same colour category as D-type asteroids, outer solar system comets, and the previous interstellar comet 2I/Borisov. The red colour is generally attributed to the presence of tholins, complex organic compounds produced when simple carbon-bearing and nitrogen-bearing molecules are irradiated by ultraviolet light and cosmic rays over long periods of time. Tholins are common in the outer solar system, on the surfaces of objects like Pluto and many Kuiper Belt comets. Their presence on 3I/Atlas is consistent with a body that spent a long time in the cold, radiation-rich environment of interstellar space. There was also the spin. Observations conducted between July 2nd and July 29th, 2025, by a team using multiple ground-based telescopes including the Southern African Large Telescope and the Nordic Optical Telescope, found a rotation period for 3I/Atlas of approximately 16.16 hours, with a brightness variation of about 0.3 magnitudes consistent with a rotating, non-spherical nucleus. That spin rate is broadly consistent with other active comets we've studied in our own solar system. Not unusual, not alarming, but the dust mass loss rates measured during that same period, ranging from 0.3 to 4.2 kilograms per second, were, as the researchers noted, higher than initially expected for an interstellar object at that distance from the Sun. Active, more active than predicted, which brought researchers back, again and again, to the same fundamental puzzle. Something was driving this comet's unusual early activity, far from where solar heating should have been powerful enough to produce it. By late July, the Vera C. Rubin Observatory in Chile, still in its early commissioning phase but already turning its enormous mirror toward interesting objects, had measured the growth of 3I/Atlas's coma. It had expanded from approximately 13,040 kilometers in diameter on June 21st to approximately 18,760 kilometers by July 2nd. The coma was growing rapidly as the comet fell toward the inner solar system. By late August, something had shifted. The sunward plume that had puzzled observers in early Hubble images was still present, but a clear anti-solar tail, a tail pointing directly away from the sun, as all proper comet tails should, had developed. On August 27th, the Gemini South Telescope in Chile captured images that showed this tail clearly, and astronomers took note. By late August, 3I/Atlas looked, in broad strokes, like a comet, but the details still didn't quite add up. The CO2 to water ratio was still anomalous. The dust grain sizes, measured from the shape and brightness of the coma, suggested relatively large particles, several micrometers in radius, which behaved differently under solar radiation pressure than the smaller grains more typical of inner solar system comets. The anti-solar tail was broad and diffuse in a way that suggested these large, slowly moving dust particles, and then there was the nickel. Spectroscopic observations detected the presence of nickel atoms in the coma of 3I/Atlas. Nickel had been detected in Comet Coma before. It was a surprising discovery first made just a few years earlier in observations of solar system comets, and it became a minor puzzle of its own, because the temperatures at the distances where comets are typically observed should be far too low to vaporize the metallic grains that would release nickel atoms as gas. In 3I/Atlas, the nickel detection was accompanied by an unusual ratio. There was significantly more nickel than iron in the coma, a ratio more consistent with industrially produced nickel alloys, as one researcher would later point out, than with naturally occurring astronomical materials where iron and nickel generally track together. The significance of this ratio was disputed. Natural explanations existed, but it was another data point in a growing list of things about 3I/Atlas that didn't quite fit the established model of how a natural interstellar comet should behave. The object was also displaying extreme negative polarization, an unusual optical property of the light scattered by dust in the coma, with a low inversion angle. These polarimetric properties place 3I/Atlas in a category distinct from most solar system comets, suggesting something different about the physical properties of its dust grains, not impossible for a natural object, but unusual. By the time astronomers at Kitt Peak Observatory in Arizona conducted spectroscopic observations of 3I/Atlas in early August, they had found something else. The comet was significantly depleted in carbon chain molecules, the organic compounds that typically produce the green fluorescence seen in many comets. 3I/Atlas was described as one of the most carbon chain depleted comets known, and then, In September 2025, it turned green. During the total lunar eclipse of September 7th, astrophotographers in Namibia, taking advantage of the unusually dark skies produced by the fully eclipsed moon, captured images showing 3 Atlas glowing a vivid, unmistakable green. Green comets are not unprecedented. The colour usually comes from diatomic carbon, 2 carbon atoms bonded together, designated C2, which fluoresces green when exposed to ultraviolet light from the sun. But 3 Atlas had just been measured as unusually depleted in carbon chain molecules. Where was the green coming from? Several explanations were proposed. One possibility was that the green glow represented deeper layers of ice being exposed as the comet approached the sun, and surface sublimation revealed progressively fresher material. Another possibility, raised by researchers including Avi Loeb in a blog post shortly after the eclipse images circulated, was that the colour was coming not from diatomic carbon, but from cyanide, HCN, hydrogen cyanide, whose production had been rising sharply as measured by the James Clerk Maxwell telescope in September 2025. Cyanide can produce a greenish fluorescence under certain conditions. The green glow was beautiful. It was also in the context of everything else that was strange about 3 Atlas, one more thing that didn't resolve cleanly into a simple explanation. To understand the debate that was building around 3 Atlas, you need to understand the man at the centre of it. Avi Loeb is not a fringe figure. He is the Baird Professor of Science at Harvard University. He was the founding director of Harvard's Black Hole Initiative and served as director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He chaired Harvard's astronomy department from 2011 to 2020, making him one of the longest-serving department heads in that institution's history. He served on the President's Council of Advisors on Science and Technology. He chaired the Board on Physics and Astronomy of the National Academies of Sciences. His publication record runs to hundreds of peer-reviewed papers. His work spans black hole physics, the early universe, the nature of dark matter, and increasingly, over the past decade, the question of whether we are alone in the cosmos. Loeb became a globally recognizable name in 2018 when he co-authored a paper in the Astrophysical Journal Letters, arguing that the peculiar behavior of the first interstellar object, Oumuamua, could be explained by a thin artificial structure, a light sail, being pushed by solar radiation pressure. The paper was published in one of the most prestigious journals in astrophysics. It was also controversial enough to generate a response that went well beyond scientific disagreement. Oumuamua had displayed a non-gravitational acceleration as it departed the solar system. It was moving faster than gravity alone could explain. Natural explanations were proposed. Outgassing, though no outgassing was detected. Pressure from solar photons on an unusually flat object. Other exotic natural mechanisms. Loeb argued that a light sail fit the data at least as well as any natural explanation, and that refusing to consider it was a failure of scientific open-mindedness rather than a demonstration of rigour. In 2021 he published a book, Extraterrestrial, the first sign of intelligent life beyond Earth, which laid out his thinking at length. And he founded the Galileo Project at Harvard, installing cameras, radio sensors, infrared detectors, and audio sensors on the roof of the Harvard College Observatory, building a systematic observational apparatus designed to look for technological signatures from space, rather than simply assuming that anything we observed had a natural origin. He had been building to 3 Atlas for years, and when it appeared on July 1st, 2025, he moved quickly. On July 16th, 2025, just 2 weeks after the discovery, Loeb, along with colleagues Adam Hibbard of the Initiative for Interstellar Studies and Adam Crowell, uploaded a preprint to the Archive preprint server titled simply, "Is the interstellar object 3 Atlas alien technology?" The paper was not peer-reviewed at the time of posting. It has become something of a lightning rod in the months since, quoted by scientists who consider it irresponsible speculation, and by science communicators who consider it a necessary thought experiment. Reading it carefully, as the paper's authors intended, it sits somewhere more nuanced than either camp gives it credit for. The paper's central structure is this. It takes seriously the hypothesis that 3I/Atlas is a functioning technological artifact and works through the orbital mechanics of what such an object might do. It uses trajectory analysis software called OITS, Optimum Interplanetary Trajectory Software, to model what maneuvers an advanced spacecraft on 3I/Atlas's orbital path might be able to execute, and it identifies several features of the object's trajectory that would be, as the authors put it, of benefit to an extraterrestrial intelligence. The first feature Loeb and colleagues focused on was the trajectory alignment with the ecliptic plane. Our solar system is roughly flat, the 8 planets, thousands of asteroids, and the vast majority of the debris that orbits our sun all move within a relatively thin disk called the ecliptic plane. This plane is a legacy of the original protoplanetary cloud that the solar system condensed from. Everything that formed from that rotating disk inherited its geometry. Interstellar objects should not care about our ecliptic. They come from other star systems with their own planes, their own orientational history, their own rotational axes. If you were to draw a random interstellar visitor's trajectory through the galaxy, there's no particular reason it should happen to enter our solar system flying in the same plane as our planets orbit in, but 3I/Atlas does. Its retrograde trajectory, it orbits in the opposite direction to the planets, which is itself unusual but not unprecedented for objects on hyperbolic paths, is aligned with the ecliptic plane to within approximately 5 degrees. The probability of a randomly directed interstellar object arriving with that degree of alignment, Loeb calculated, is roughly 0.2%, 1 in 500. That alone is not alarming. Rare events happen. But Loeb did not stop there. He then examined the close approaches that 3I/Atlas made to the inner planets on its trajectory through the solar system. Planets move. They sweep around their orbits at different speeds, at different distances from the Sun. When an object passes through the inner solar system, there's no guarantee that the planets will be anywhere near it. Jupiter takes 12 years to orbit the Sun. Mars takes about 687 days. Venus takes 225 days. For all three of them to be in positions relatively close to where 3I/Atlas was passing, when 3I/Atlas was passing there, that requires a certain alignment of timing. 3I/Atlas passed within approximately 29 million kilometers of Mars on October 3rd, 2025. It made a relatively close approach to Venus. It passed at a distance from Jupiter that was within a few times the size of Jupiter's gravitational sphere of influence. Loeb calculated the combined probability of an interstellar object on a random trajectory making close approaches to all three of those planets, accounting for where the planets actually were in their orbits when 3I/Atlas arrived, at approximately 0.005%, 1 in the 20,000. He then added the perihelion timing. 3I/Atlas reached its closest approach to the Sun, perihelion, on October 29th, 2025. On that date, Earth was on the exact opposite side of the Sun. The Sun stood directly between Earth and 3I/Atlas. The comet was in solar conjunction, completely hidden from every ground-based telescope on Earth, and difficult even for space-based observatories to observe, due to the overwhelming brightness of the nearby solar disk. Loeb pointed out that perihelion is the optimal moment for a spacecraft to perform a significant orbital maneuver. It's the point of maximum speed, maximum gravitational force, minimum orbital energy. If you wanted to dramatically change your trajectory, to transition from a hyperbolic escape path to an elliptical bound orbit around the Sun, for example, or to execute a sharp turn. Perihelion is where you do it, because that's where the energy available to you is greatest. This is a principle called the Oberth effect, after Hermann Oberth, one of the founding theorists of rocketry. Normally, spacecraft use the Oberth effect to gain speed, firing engines at perihelion to maximize the change in velocity, but the same mathematics works in reverse. You can fire engines at perihelion to slow down, to bleed off velocity, and let the sun's gravity capture you into a permanent orbit. Loeb called this a reverse solar Oberth maneuver, and he argued that if 3I/ Atlas were a technological object wanting to transition from an escape trajectory to a bound orbit, October 29th, hidden from Earth's view behind the sun, would be the optimal moment to do it. The probability that an object's perihelion would fall precisely when Earth is on the opposite side of the sun adds yet another layer to the stack of improbabilities, not vast on its own, but part of a compounding picture. Loeb stacked all of these together: the ecliptic alignment, the 3 planetary close approaches, the perihelion timing, and calculated a combined probability that all of them would occur by chance at something approximating 1 in the 20,000 or lower, depending on exactly how the calculation was structured. And he noted that 1 in 20,000 is not impossible, but it is unusual enough to at least ask whether coincidence is the right word. He drew a comparison. If you walk into a casino and watch someone roll double sixes 10 times in a row, you don't automatically conclude the dice are loaded. But you probably want to take a look at the dice. The odds are astronomical, but technically achievable by chance. The question is whether you accept the improbability or investigate it. The paper went further. It invoked the dark forest hypothesis, a concept derived from the science fiction of Chinese author Liu Cixin, though the underlying logic predates the novels, which proposes that the universe's apparent silence, the fact that we have not detected alien civilizations despite the statistical likelihood of their existence, may be explained by a kind of cosmic predator-prey dynamics. Every civilization that makes itself known creates the risk of being targeted by another civilization that views all potential competitors as existential threats. So civilizations go silent and destroy any emerging intelligence they encounter, precisely to avoid mutual catastrophe. In this framework, an interstellar object approaching our solar system might not be a passive comet. It might be a scout, a probe, a weapon, and the perihelion maneuver, if one occurred, would be the moment of commitment, the moment where an object that was merely passing through became something that was staying. Loeb was careful, throughout the paper and in his public statements, to frame all of this as a hypothesis worthy of investigation, rather than a conclusion. He explicitly stated that 3I/ Atlas was most likely a natural interstellar comet. He wrote that the technological hypothesis was being explored as a pedagogical exercise with potentially serious consequences, and that the authors of the paper did not necessarily ascribe to the hypothesis themselves, but he also said that the potential consequences, if the hypothesis turned out to be correct, could be significant enough to justify serious attention regardless of the low probability. A 1% chance of something catastrophic warrants more preparation than a 99% chance of something benign. That at least is the logic he offered. The paper circulated widely on social media and in science communication channels within hours of being posted. By autumn 2025, it had been covered by every major science outlet on the planet, and the scientific community's response was, in many cases, not gentle. The scientific community has a word for claims that propose extraordinary explanations for phenomena that have ordinary ones. The word is not polite. Chris Lintott, an astronomer at the University of Oxford and one of the most recognisable science communicators in the United Kingdom, called the alien technology hypothesis for 3I/ Atlas simply absolute nonsense. He argued that proposing exotic explanations for phenomena that had straightforward natural interpretations was bad science, not just wrong, but methodologically backwards. You start with the simplest explanation consistent with the data, not with the most dramatic one. Tom Statler, NASA's program scientist for small bodies, maintained consistently and publicly that all available evidence pointed to 3I/Atlas being a natural comet. Everything observable about it, the brightness, the outgassing pattern, the development of a tail, the coma morphology, the chemical signatures, Zhenbuan was consistent with a comet. Not identical to any comet we'd studied before, because no comet we'd studied before had spent billions of years in interstellar space, but consistent with the broad category of naturally occurring icy bodies behaving as naturally occurring icy bodies behave when they approach a star. Penn State astronomer Jason Wright, who focuses on extrasolar planets and the search for extraterrestrial intelligence and takes that search very seriously, wrote a detailed blog post working through each of Loeb's listed anomalies and providing natural explanations for them. Wright concluded that 4 of the anomalies were genuinely of scientific interest: the high nickel abundance, the extreme polarization properties, the unusual water ratios, and the early brightening activity. These were, he said, the sorts of anomalies one expects from a new kind of comet. Unusual, deserving of investigation, but not evidence of artificial origin. Wright's broader point was methodological. He noted that none of Loeb's anomalies had been predicted in advance. That is, Loeb had not said before the discovery, "Here are the things I expect to find if 3I/Atlas is a spacecraft," and then found them. Instead, the anomalies were identified after the fact and then assigned probabilities. When you work that way, when you find surprising data, and then calculate how unlikely it is, you run the risk of overstating the significance, because you're essentially selecting the most extreme features of the data and asking how unlikely they are individually, without accounting for how many features you looked at and how many of them were ordinary. This is sometimes called the Texas sharpshooter fallacy, after the image of someone who fires a shotgun at a barn wall and then draws a target around wherever the pellets happen to cluster. The clustering looks significant until you realize the target was drawn after the fact. A Princeton astrophysics professor made a similar point, noting that given the number of things one could potentially notice about any complex object, finding a handful of unusual features and assigning them dramatic probabilities doesn't constitute evidence in the scientific sense. It constitutes a list of interesting questions. The concern within the SETI community, the researchers actually dedicated to the serious methodical search for extraterrestrial intelligence, was more institutional. Organizations like the SETI Institute have spent decades building credibility for the proposition that searching for alien life is legitimate science, not science fiction. They operate under strict protocols about when and how to make claims. Their approach is deliberately conservative, precisely because the stakes of a false positive are so high. Making a claim about alien contact that turns out to be wrong does lasting damage to the entire enterprise. Loeb's approach was, from their perspective, the opposite of conservative. He posted a preprint 2 weeks after discovery, before almost any meaningful observational data had been collected, arguing that the object could be alien technology. And then he posted updates, week after week, identifying new anomalies, proposing new interpretations, giving interviews on Fox News and to news outlets around the world. Each post generated headlines. Each headline reinforced the alien narrative in public conversation, regardless of what the scientific data was actually saying. Researcher Bayer analysed the social media footprint of 3I/Atlas and found that approximately 280,000 of the 700,000 posts about the Comet on X invoked aliens or alien technology, roughly 40% of all discourse about the object. Approximately 130,000 posts referenced Loeb by name or as a Harvard scientist. Over 82,000 posts explicitly paired his name with the alien technology hypothesis. Bayar noted that Loeb did, at times, state clearly that 3I/Atlas was most likely a natural interstellar comet, but this caveat was buried. Loeb spent far more time walking through the supposed anomalies and entertaining the alien technology hypothesis. For most audiences, the volume and emphasis of that speculation effectively buried the initial caveat and recentered the story around the alien frame rather than the natural comet explanation. The pattern critics identified was this. Each time data came in that explained one of Loeb's anomalies, he added new ones. The list grew from 5 anomalies to 8, from 8 to 12, from 12 onward. The alien hypothesis was structured in a way that couldn't be falsified in the short term, because there would always be some new observation that hadn't been explained yet, and that gap could always be filled with speculation. But Loeb had answers for all of this, and they were not without substance. His core methodological argument was this: science is supposed to follow the evidence, not the consensus. When a piece of data is unusual, the correct scientific response is to investigate, not to assume that a familiar explanation applies. The history of science is full of cases where the consensus was wrong, where the evidence pointed somewhere uncomfortable and the scientific establishment resisted going there until the data became overwhelming. He was right that this happens. Continental drift was dismissed for decades by mainstream geology. The idea that stomach ulcers were caused by bacteria, Helicobacter pylori, now standard medical knowledge, was greeted with hostility and derision when Barry Marshall and Robin Warren proposed it in the 1980s. Marshall infamously infected himself with the bacteria to prove the point. They later won the Nobel Prize. Loeb's point was not that 3I/Atlas was definitely a spacecraft. His point was that we shouldn't close the investigation before the evidence was in, and that the accumulated list of unusual features was at least sufficient to justify continued, careful observation. This was, in the abstract, a reasonable scientific position. His second argument was about consequences. Even if the probability of the alien technology hypothesis ceased being correct was 1%, or 0.1%, the implications of being wrong, of dismissing a genuine alien probe without investigation, would be enormous. The asymmetry between the cost of being wrong and the cost of being right justified treating the hypothesis with seriousness, even under conditions of very low probability. There is a version of this argument that most scientists would accept. The question is where the line falls between healthy open-mindedness and unfalsifiable speculation, dressed in the language of science. The debate never fully resolved. It was still ongoing when 3I/Atlas disappeared behind the sun on October 29th, 2025. What happened next would add another layer to the argument, because even behind the sun, we were watching. NASA's Parker Solar Probe was in a position to observe 3I/Atlas during the period when it was hidden from Earth-based instruments. The probe, designed to study the sun from close range, carries a wide-field camera called WISPR, Wide Field Imager for Solar Probe, that operates in visible light and can detect faint objects against the solar background. From October 18th through November 5th, 2025, Parker captured approximately 10 images per day of 3I/Atlas as the comet moved through its field of view, positioned at distances between 172 and 195 million miles from the target. The ESA/NASA Solar and Heliospheric Observatory, SOHO, also had 3I/Atlas in its field of view around this time. It had been expected to be too faint for SOHO to detect, but detailed image processing and overlaying of stacked telescope images ultimately produced a detection. None of the observations made during the perihelion passage showed any evidence of a maneuver. No change in trajectory, no emission of non-natural energy, no signals. Nothing that couldn't be explained by a comet behaving like a comet. When 3I/Atlas emerged from behind the sun in early November 2025, and observations from ground-based telescopes resumed on October 31st, the first astrometric measurements confirmed the expected. 3I/Atlas was still on its hyperbolic trajectory. Its orbital eccentricity was unchanged. It had not slowed down. It had not captured itself into a bound orbit around the Sun. It was leaving. Loeb acknowledged this. He updated his probability assessments, but he also identified new anomalies in the data that had been collected during the perihelion approach, and he framed each of them in the same way. Interesting, worth investigating, not conclusively natural. The debate, in other words, continued exactly as it had before, because 3I/Atlas had one more thing to show the world before it faded from view. The Mars encounter happened on October 3rd, 2025, before 3I/Atlas disappeared behind the Sun. 3I/Atlas passed within approximately 29 million kilometers of Mars, close enough in astronomical terms to be called a near encounter, even if that phrase loses some of its drama when you picture 29 million kilometers as a physical distance. It's about 75 times the distance from the Earth to the Moon. In the vast emptiness of the solar system, it's a near miss. NASA was ready. The Mars Reconnaissance Orbiter, carrying its powerful HIRIS-E camera, the High Resolution Imaging Science experiment, which was designed to photograph the Martian surface at resolutions fine enough to resolve individual boulders and rover tracks, was redirected to look at 3I/Atlas during its closest approach. At that distance, HIRIS-E could not resolve individual surface features on the comet, but it could separate the nucleus from the surrounding coma with greater precision than most Earth-based instruments, and it could give scientists a better estimate of the nucleus size. ESA's 2 Mars missions, Mars Express and the ExoMars Trace Gas Orbiter, also made observations around this time, using spectrometers to analyze the chemical signatures of 3I/Atlas from their vantage point in Mars orbit. ESA's Planetary Defense Office used data from the ExoMars Trace Gas Orbiter to improve the comet's predicted orbital position by a factor of 10, a significant refinement that tightened the constraints on its future trajectory. The Mars flyby produced useful data. It did not produce any evidence of anything unusual. No secondary objects were detected separating from 3I/Atlas. No anomalous signals. No evidence of propulsion. Just a comet on its expected path, shedding gas and dust as it fell toward the Sun, passing close to a planet that was observing it, but getting no response in return. Loeb had suggested in advance that the Mars encounter might be an opportunity for a hypothetically technological 3I/Atlas to deploy something. A probe, a scout, a smaller vehicle released with a velocity adjustment of a few kilometers per second that could intercept Mars or enter Martian orbit. He noted that such an object would be too small to detect at that distance with current telescopes, and that Mars orbiters were positioned to notice anything that arrived. Nothing arrived. The Mars orbiters reported nothing anomalous. The encounter passed, and 3I/Atlas continued on its path toward the Sun. But the October 3rd Mars encounter did establish something useful. The observations gave scientists one of their clearest views yet of 3I/Atlas's physical state before perihelion. The comet was active. Its coma was bright and extended. Material was flowing off the nucleus at a steady rate. It was behaving in all observable ways like a comet approaching a star, which is, after all, exactly what it was doing. Then came the perihelion, then the weeks of solar conjunction, then the re-emergence. When 3I/Atlas came back out from behind the Sun in early November 2025, the world's telescopes turned back to it, and what they saw in the high-resolution post-perihelion images from the Hubble Space Telescope was genuinely unexpected. Hubble's post-perihelion observations, taken in November and analysed in the weeks that followed, showed 3I/Atlas in a highly active state, which was expected after perihelion when a comet has received maximum solar heating and is at its most volatile. The coma was bright. Her tail was clearly visible and well developed. Standard comet behaviour, but the jet structures were not standard. Using specialised image processing techniques, researchers examined the fine structure of the inner coma, the region immediately surrounding the nucleus, and identified a system of 3 mini-jets. 3 separate streams of ejected material, each distinct, emerging from the nucleus in 3 different directions. The 3 jets were separated by approximately 120 degrees from each other. Each one was separated from its neighbour by 1/3 of a full circle. This gave the 3-jet system a striking symmetry. It was, in geometric terms, as close to perfectly uniform as it could be. 3 vectors pointing outward from a central point, equally spaced, forming an equilateral triangle if you connected their tips. In natural comets, jets arise from patches of ice that are exposed directly to solar radiation and begin sublimating when the sun's heat penetrates the surface material. The pattern of jets on a natural comet reflects the distribution of those ice patches across the nucleus surface, combined with the rotation of the nucleus and the varying intensity of solar heating at different points on the surface. Natural jet systems are complex, asymmetric, evolving over time as surface composition changes and as different patches of ice are exposed and depleted. They are not typically symmetric, to within the precision of what was observed in 3 ice/atlases post-perihelion data. Loeb wrote about this finding in November 2025, noting that the 3-jet system, separated by 120 degrees with unusual regularity, stood in stark contrast to the chaotic and irregular jets normally produced by sublimating ice on natural cometary bodies. He drew a comparison to engineered thruster systems, where symmetrical arrangements serve functional purposes, providing balanced force without net rotational torque, optimizing stability, enabling controlled orientation. Other researchers were more cautious. Independent observations had documented a wobbling high-latitude jet before perihelion, with periodic modulation consistent with nucleus rotation. The argument was that complex but natural processes could produce unexpected geometric patterns, particularly if the nucleus had an unusual shape or an unusual distribution of volatile ices that happened to place active sublimation regions at symmetric points. This is not impossible. Nature produces symmetry regularly. The hexagonal cells of a honeycomb, the spiral arms of galaxies, the bilateral symmetry of living organisms. Symmetry emerging from natural processes is not itself evidence of design, but the specific precision of the 120-degree separation, combined with everything else that was already unusual about 3 ice/atlas, made it another entry in a list that kept growing longer. The sunward jet was also still present in the post-perihelion images. In November 2025, 3 ice/atlas continued to show an anti-tail, a jet or stream of material pointing toward the sun rather than away from it. In most comets, material is pushed away from the sun by solar radiation pressure and solar wind. A sunward extension is unusual. It had been present in the July and August 2025 images as well, though some astronomers argued those early appearances could be explained by the viewing geometry. If the anti-solar tail was pointing almost directly away from Earth as well as away from the sun, it would appear foreshortened and potentially invisible, while any material being ejected in other directions might appear to be pointing sunward in projection. Loeb argued in multiple posts that the sunward jet in the November observations could not be dismissed as a geometric artifact, because the viewing geometry in November was different from July and August. Others disputed this interpretation. The November images also showed the X-ray glow. In late November and early December 2025, the XRISM telescope, a Japan-led X-ray telescope with ESA and NASA contributions, and the XMM Newton X-ray Observatory both observed 3 ice/atlas. What they found was a diffuse X-ray glow surrounding the comet nucleus. X-ray emission from comets is a known phenomenon in solar system objects. It was discovered in comet Hyakutake in 1996, which was a genuine surprise at the time, and it has since been detected in many solar system comets. The mechanism is called charge exchange. Highly ionized particles in the solar wind collide with neutral atoms and molecules in the comet's coma, and the resulting charge transfer releases X-rays. It's a physical process that requires a coma of neutral gas and a solar wind, and 3I/Atlas had both. But 3I/Atlas was the first interstellar comet to ever be observed in X-ray light. That distinction was noted by ESA in its reporting on the observation, not because X-ray emission from an interstellar comet implies anything unusual. The mechanism is the same regardless of where the comet came from, but because it was a first, and because the energy and spatial distribution of the X-ray glow provided additional diagnostic information about the density and composition of 3I/Atlas's coma. None of the post-perihelion data provided evidence of artificial origin. Not the three-jet system, not the sunward extension, not the X-ray glow. Each feature had at least one plausible natural explanation, but each feature also added to the texture of an object that seemed determined to remain just unusual enough to keep the conversation going. ESA's Jupiter Icy Moons Explorer, known as JUICE, made observations of 3I/Atlas between November 2nd and November the 25th, 2025. JUICE was en route to Jupiter and was positioned in a part of the solar system that gave it a favourable view of 3I/Atlas as the comet emerged from solar conjunction. JUICE carried multiple instruments including cameras, spectrometers and particle detectors, and its observations from this period were expected to contribute significantly to the overall scientific picture. However, JUICE's data transmission rate is limited. The spacecraft was still using a low bandwidth antenna during this phase of its mission, and the full results were not expected to be returned and analysed until February 2026. In the meantime, other observations continued. The Hubble Space Telescope re-observed 3I/Atlas on November 30th, 2025, using its Wide Field Camera 3, at a distance of approximately 178 million miles from Earth. The comet appeared as a bright dot with a light blue halo, the inner coma catching the sun's light, while background stars appeared as diagonal streaks because Hubble was tracking the comet's motion rather than the stars. NASA's TESS satellite, the Transiting Exoplanet Survey satellite, normally used to detect planets around other stars, made special observations of 3I/Atlas in the weeks after perihelion, contributing to the study of the comet's activity level and rotation. SPHERE-X, a NASA infrared survey mission launched in early 2025, turned its infrared detectors on 3I/Atlas in December, measuring the infrared emission from dust, water, organic molecules, and carbon dioxide in the coma, and adding another layer to the already rich chemical data set. The picture that emerged from all of this was of an object that had survived its closest approach to the Sun and was now outbound, cooling down, gradually becoming less active, the rate of outgassing declining as it moved farther from the solar heating that was driving it. A comet on its way home, in the sense that any interstellar object has a home, the dark cold expanse between the stars. And through all of it, the scientific argument continued, not loudly, by December. The most intense phase of the debate had been during the autumn months, before and around perihelion. By December, most of the astronomical community had moved toward a clear consensus position. 3I/Atlas was a natural interstellar comet. Unusual chemistry, interesting jet structures, scientific value that would take years to fully extract from the data, but natural. Loeb continued to write. He continued to identify new anomalies. He began, in late 2025 and into early 2026, to shift some of his focus toward a related but distinct possibility: panspermia. The idea that 3I/Atlas might be carrying life, microbial life, spores, complex organic molecules at the edge of biology, between star systems. Not a spacecraft, not technology, but not simply a dead rock either. It was a quieter hypothesis than the alien technology proposal. It generated fewer headlines, but it was in some ways more scientifically grounded, because we already know that organic molecules are widespread in space, that comets can carry them, and that there are serious scientific discussions about whether life could have been seeded from one planetary system to another on the surfaces of interstellar objects. The story of 3I/Atlas was not over, but one of its most dramatic chapters was closing. The object was heading for Earth. The winter of 2025 was, for anyone following the story of 3I/Atlas, a period of quiet intensity. The loudest phase of the debate had passed. The perihelion had come and gone. The comet had emerged from behind the sun, still outbound, still a comet, and the scientific community had largely returned to its normal register, careful, methodical, interested, but not alarmed. But the data kept coming. Every week brought new papers posted to Archive, the pre-print server where astronomers share results before formal peer review, photometric analyses examining the comet's brightness evolution, polarimetric studies examining how 3I/Atlas scattered light at different angles relative to the sun, chemical analyses probing the relative abundances of the molecules detected in the coma by Webb and other instruments, orbital refinements incorporating thousands of new position measurements. The picture assembled by all of this work was becoming more detailed, more nuanced, and in some ways more puzzling, not in the direction of alien technology, but in the direction of genuinely unusual natural chemistry. One paper examined the nickel-to-iron ratio in more detail. Nickel in Komutra Komai had been a puzzle since its discovery in solar system comets only a few years earlier. The mechanism by which nickel atoms enter the gas phase at temperatures far too low to directly vaporize metallic grains is still not fully understood. The most widely accepted model involves the photodissociation of an organometallic precursor molecule, a compound that contains nickel bonded to organic molecular groups, which breaks apart when hit by ultraviolet radiation from the sun, releasing the nickel atom into the gas phase. If that's the mechanism, then the ratio of nickel to iron in a comet's coma tells you something about the ratio of nickel-bearing to iron-bearing organometallic precursors in the nucleus. In 3I/Atlas, the nickel-to-iron ratio was unusually high, more nickel than iron. The mainstream interpretation was that this reflected the specific chemistry of the organic compounds in 3I/Atlas's nucleus, chemistry that had evolved under conditions different from those that produced the nickel-iron balance in solar system comets. Not impossible, not alarming, but unusual enough that several groups were working to characterize it more precisely. The high CO2 to water ratio received additional scrutiny as well. Several papers explored the carbon isotope ratio in 3I/Atlas's CO2, specifically the ratio of carbon-13 to the more common carbon-12. This isotope ratio is a tracer of the environments in which the carbon was incorporated into molecules. Stars process carbon through nuclear, burning in different proportions depending on their mass and age, and the carbon-13 to carbon-12 ratio in the interstellar medium varies across different regions of the galaxy. The Webb telescope had detected the signature of heavy CO2 containing carbon-13 in 3I/Atlas's coma, though quantifying the isotope ratio was complicated by dust and other gases that partially obscured the signal. If the isotope ratio could be precisely measured, it might narrow down the type of stellar environment in which 3I/Atlas formed, whether the carbon in its nucleus was produced in old metal-poor stars from the early galaxy, or in more recent stellar generations. That would be an extraordinary measurement, an isotopic fingerprint of another solar system. The analysis was ongoing as the comet moved outbound. There was also the polarization. 3I/Atlas showed extreme negative polarization at small phase angles, the angles between the sun, the comet and the observer. Polarization of scattered light is a sensitive probe of the physical properties of the scattering particles, their size distribution, their shape, their composition, their structure. Solar system comets show a characteristic polarization curve that varies with phase angle in ways that have been well studied and modelled. 3I/Atlas's polarization was at the extreme negative end of the range observed in any comet, with a lower inversion angle than typical. This was consistent with the dust grains having unusual optical properties, possibly related to their size, possibly to the presence of unusual organic compounds, possibly to some combination of factors that hadn't been fully modelled. Several research groups were working on models that could reproduce the observed polarization signature. The initial conclusion was that the dust was genuinely unusual, in ways that were consistent with a formation environment different from our solar system, but not in ways that required any non-natural explanation. The full picture of 3I/Atlas's composition that had emerged by the end of 2025 was of a comet from a chemical environment unlike any we'd directly sampled before, rich in CO2 relative to water, carrying organic compounds with unusually high nickel content, displaying dust with optical properties at the edges of what solar system comets produce, covered in foldings that told the story of billions of years of radiation processing. It was, in other words, genuinely alien. Not in the science fiction sense, but in the precise scientific sense of having originated in conditions fundamentally different from those that shaped the objects we'd previously studied. An alien comet, a natural one, but alien in the sense that mattered scientifically, different enough to push the boundaries of the models we'd built from studying our own solar system's inventory. David Jewitt, who had led the Hubble observations, put it simply. "We've crossed a threshold," he said. "Objects like this have been passing through the solar system since its formation. We're only now building the tools to see them, and what we're finding in those first careful looks is that the universe's diversity runs deeper than the neighbourhood we grew up in." He was right, and the neighbourhood was about to offer one more close look. Some nights are made for this kind of thinking, the kind of night where the sky is genuinely dark, no city lights bleeding upward, no moon, just the full depth of the Milky Way arching overhead, the kind of density of stars that you don't believe until you're actually under it, the kind of dark that makes you feel, physically, the scale of the space above you. In that kind of darkness, a point of light that is coming from another star means something different than it does in an astronomy paper. It's not an object class. It's not an orbital eccentricity. It's a piece of another world, travelling through the dark, arriving in our sky. Thousands of people around the world pointed telescopes at 3I/Atlas between July and December of 2025. Professional astronomers with instruments worth hundreds of millions of dollars. Amateur astronomers with 8-inch reflectors on garden mounts. Astrophotographers with tracked cameras and narrow-band filters. The Virtual Telescope Project ran live broadcasts of 3I/Atlas's closest approach to Earth on December 20th, 2025, streaming images of the comet in real time to hundreds of thousands of viewers around the world. You could watch it move. Over the course of a single night's observation, you could see it shift position against the background stars, the visual proof of its extraordinary speed. Most objects in the sky are so far away that their motion is imperceptible on human timescales. 3I/Atlas moved fast enough that a careful observer could detect its motion over the course of an evening. There's something about that visibility, that tangibility, that the numbers don't quite capture. 58 kilometers per second is a statistic. Watching the comet move across the star field in real time is an experience. The experienced amateurs who observed 3I/Atlas during its closest approach in December knew they were seeing something that would not come again. Not this object. It was already leaving. Not even a similar object necessarily, in any predictable time frame. Interstellar visitors are rare enough to be meaningful. The next one might arrive next year, or in 5 years, or in 50. And it would be different. Different chemistry, different origin, different history. Unique. 3I/Atlas was this. One chance, one pass, and then gone. The astronomical community processed its observations with the urgency that entailed. Papers were written fast, data was shared widely. The Minor Planet Center's tracking of 3I/, Atlas incorporated contributions from observatories on every inhabited continent. The analysis of Webb's spectroscopic data involved scientists from multiple institutions in multiple countries working in parallel. The Hubble observation campaigns were coordinated with ESA, with the data processed at STSCI in Baltimore and made publicly available within weeks. The collaboration was not seamless. Scientific collaboration never is. But it was real, and it was broader and faster than most interstellar object studies could have been even a decade earlier. The infrastructure for rapid international scientific response to unexpected astronomical events has improved substantially. 3I/Atlas was a test of that infrastructure, and by most assessments it passed. End of expansion section. Something is heading into our solar system, and scientists can't agree on what it is. Full sleep documentary script. Part 6 of 9. Heading for Earth is not quite the right phrase, but it's close enough to create a pause. On December 19th, 2025, 3I/Atlas made its closest approach to our planet. The distance was approximately 270 million kilometers, 1.8 astronomical units, or about 168 million miles. To put that in perspective, that's roughly 700 times the distance from Earth to the Moon. It's further than Earth is from the Sun. At that distance, 3I/Atlas was never a threat in any physical sense. No possibility of collision, no danger of any kind. But 270 million kilometers was for an interstellar object close. Closer than almost anything from outside our solar system has ever come. And the timing, with the comet at maximum observational accessibility, after emerging from solar conjunction, still active, still bright, still shedding material, made December 2025 one of the best windows humanity would ever have to study something that came from another star. Professional and amateur astronomers around the world made use of it. The Subaru telescope at Mauna Kea, Hawaii, pointed its focus instrument, the faint object camera and spectrograph, at 3I/Atlas at morning twilight on December 13th, 2025. The resulting image, taken 6 days before closest approach, showed the comet clearly. A bright central condensation, a visible coma, and a distinct tail extending away from the Sun. It was by that point a recognizable comet. Unmistakably cometary in appearance, the image was striking in its clarity. What struck astronomers looking at these late-stage images was not the strangeness but the familiarity. 3I/Atlas, by December, looked like a comet. It had a tail. It had a coma. It was shedding volatiles in the expected direction. The features that had made it seem unusual, the early sunward plume, the ambiguous coma structure, the lack of a clear anti-solar tail, had largely resolved into ordinary cometary behaviour as it got closer to the Sun and solar heating intensified. The scientific consensus, stated clearly in a NASA press briefing in late 2025, was unambiguous. Tom Statler put it directly. It looks and behaves like a comet. All evidence points to it being a comet. No technosignatures or indications of artificial origin had been found. No anomalous signals. No evidence of propulsion. No manoeuvre at perihelion. ESA agreed. The European Space Agency's assessment, based on all available trajectory, composition, and activity data, was that 3I/Atlas was consistent with natural cometary behaviour. Its chemistry was unusual by solar system standards, but explicable in terms of an object that had formed around a different star, in a different chemical environment, and had spent billions of years in interstellar space, being processed by cosmic radiation. NASA's SPHEREX mission made its observations of 3I/Atlas in December, measuring infrared emission from the comet's coma and adding to the chemical data set. The full analysis of SPHEREX data was ongoing well past the closest approach, with scientists working to extract everything they could from the infrared signatures of 3I/Atlas's dust, water, organics, and carbon dioxide. It should be said clearly, because the clarity matters. 3I/Atlas did not remain in the solar system. It did not execute a reverse Oberth maneuver at perihelion. It did not transition from a hyperbolic escape trajectory to a bound orbit. Its orbital eccentricity remained approximately 6.14, ensuring that it would continue outbound, accelerating away from the Sun, slowing only slightly as gravity pulled at it from behind, and eventually reach its hyperbolic excess velocity of 58 kilometers per second and maintain that speed indefinitely as it returned to interstellar space. It was always going to leave, and it left. What changed was our understanding of what it was made of and where it came from. The chemical data, taken together, told a coherent story. 3I/. Atlas was a comet from a solar system with different chemistry from ours, one where the building blocks of comets were richer in carbon dioxide relative to water, possibly because the object formed far from its parent star where water ice was scarce, or because it was old enough to have had its water-rich outer layers destroyed by cosmic ray processing over timescales that our solar system's comets haven't experienced. The reddish tholins on its surface told the same story. This was an ancient object shaped by billions of years of radiation. The speed of 3I/Atlas, 58 kilometers per second hyperbolic excess velocity, was itself a record. The previous fastest interstellar object, Oumuamua, had arrived at about 26 kilometers per second. Borisov came in at about 32 kilometers per second. 3I/Atlas was moving at almost twice Borisov's speed and more than twice Oumuamua's. That extreme speed tells cosmologists something about its history. The longer an object drifts in interstellar space, the more gravitational kicks it absorbs from passing stars and dense molecular clouds. Each interaction adds a little velocity. An object moving as fast as 3I/Atlas has been in interstellar space for a very long time, possibly billions of years, absorbing nudges from stellar encounters that compounded over geological timescales into the velocity we measured. The trajectory analysis never definitively identified where 3I/Atlas came from. Tracing hyperbolic trajectories backward through the galaxy is complicated by the fact that stars move, and the gravitational landscape of the galaxy shifts over millions of years. The direction from which 3I/Atlas appeared to be coming was oriented toward the dense star fields of the galactic center, which is one of the reasons it had been hard to detect before July 2025. But tracing its path back to a specific star system of origin was beyond the resolution of the available data. Its home star, if it still exists, is unknown. What we do know is that somewhere in the Milky Way, around a star we cannot identify, a process of planet formation produced a body rich in carbon dioxide, ice, and ancient organics, coated in reddish radiation processed tholins, rotating slowly on an axis that gave it a day of about 16 hours. That body was ejected from its home system, possibly by a gravitational interaction with a giant planet migrating through the protoplanetary disk, the same mechanism that ejected countless comets from our own solar system during its chaotic early history. And it travelled through the dark between the stars for what may have been longer than the Earth has existed. In the summer of 2025 it passed through our solar system. It became, for a few months, the most studied object in modern astronomy, and then it left. The closest approach on December 19th was the last good observational window. After that, 3I/Atlas began to recede. Each week it moved further from Earth, further from the Sun. Its surface cooled. The rate of outgassing declined. The coma shrank. The tail faded. By early 2026 it was visible only with substantial telescopes under dark skies. By spring 2026 it would be a point of light indistinguishable from a faint star to most instruments. But the scientific work was not over. The observations had been made. The data existed. Analysis was ongoing at dozens of institutions around the world, and one more data return was expected. ESA's JUICE spacecraft, which had observed 3I/Atlas from November 2nd through November 25th, 2025, was still transmitting that data back to Earth using its low-bandwidth antenna. The full JUICE dataset was expected to be returned and analysed by February 2026. JUICE had carried multiple instruments: cameras for imaging, spectrometers for chemical analysis, particle detectors for measuring the environment around the comet, and its observations from the post-perihelion phase, when 3I/Atlas was at its most active, were potentially among the most scientifically valuable in the entire dataset. NASA's Juno spacecraft, currently orbiting Jupiter, was also expected to observe 3I/Atlas as it passed through the region of Jupiter's orbit in early 2026, providing one more set of measurements before the comet moved too far to study effectively. The scientific community had 6 months with 3I/Atlas, from discovery in July 2025 to the last useful observations in early spring 2026. In that time, it was observed by more telescopes and spacecraft than any other interstellar object in history, by a significant margin. Hubble imaged it multiple times. Webb spectroscopically analysed its coma. Parker Solar Probe watched it through perihelion. Mars orbiters observed it during the Mars flyby. JUICE observed it post-perihelion. TESS, Sphere-X, Scirism, X-mu-M Newton, all of them pointed at this visitor from another star and added their measurements to the collective dataset. The data will take years to fully analyse. Papers will be published throughout 2026 and beyond. Some will confirm the natural comet hypothesis more firmly. Some may identify new anomalies that complicate the picture. The scientific story of 3I/Atlas is not over, even though the comet itself has moved beyond the reach of easy observation. There's a question that the story of 3I/Atlas keeps circling back to, and it's worth sitting with it for a moment before we talk about where all of this is going next. The question is, what does it mean to find something like this? Not in the scientific sense, though that's important. In the larger sense, what does it mean to discover that the interstellar medium, the vast supposedly empty space between the star, is not actually empty? That objects from other solar systems pass through ours with some regularity, carrying chemical evidence of conditions that existed billions of years ago around stars that may no longer be shining. The philosophical weight of that question is easy to miss in the rush of data and debate, but it's real. For most of human history, the stars were permanent, remote, and unreachable. The idea that something could travel from one to another was either science fiction or theological speculation. Now it's just astronomy. 3I/Atlas is made of materials that formed around another star: the water ice, the carbon dioxide, the tholins on its surface, the silicate grains in its coma. Every molecule, every atom, was assembled in a different solar system, around a different sun, under conditions we can only partially reconstruct from the signals it sent us as it passed. In a very literal sense, we received a physical sample from another star system in the 2025, not brought back by a probe, not transmitted as a signal, just arrived, announced by a faint smudge on a survey telescope image, and given to us for a few months before departing forever. Scientists often speak of interstellar objects as natural probes, not in Loeb's sense of artificial technology, but in the sense that they probe the chemistry and physics of other solar systems in ways we cannot accomplish any other way. Our fastest spacecraft, Voyager 1, which has been travelling outbound since 1977, is currently about 163 astronomical units from the Sun, roughly 24 billion kilometres. At that speed, it would take approximately 75,000 years to reach the nearest star system, Alpha Centauri, if it were even headed in that direction, which it isn't. We cannot travel to other solar systems in any practical sense. We cannot send probes there on any timescale meaningful to human civilization, but nature can, and occasionally nature does. The Vera C. Rubin Observatory represents the next chapter in this story. The Rubin Observatory is a large survey telescope in Chile designed from the ground up for the most ambitious sky survey in history, the Legacy Survey of Space and Time, which will photograph the entire accessible sky every few nights for 10 years, generating an unprecedented catalogue of everything that moves. It entered commissioning in the 2025 and was already contributing pre-discovery observations for 3I/Atlas before the human observers knew what they were looking for. Projections published in the scientific literature, drawing on estimates of the interstellar object population based on the detection of Oumuamua, Borisov, and 3I/Atlas, suggest that the Rubin Observatory will detect new interstellar objects at a dramatically higher rate than before, potentially one new interstellar object every few months, once the survey is fully operational and astronomers have developed robust detection algorithms for this category of object. That means the question of what to do when an unusual one arrives, how to evaluate it, how to study it, how to decide whether its unusual features are scientifically interesting or scientifically alarming, is going to be a practical question, not an academic one, within the next decade. Loeb's proposed Loeb scale, the 0 to 10 classification framework for interstellar objects based on how many technological anomalies they display, is one attempt to create a systematic answer to that question. Whether the astronomical community adopts it or proposes something else, the underlying need is real. We need criteria, we need protocols, we need an agreed way of deciding when an interstellar object is interesting enough to warrant maximum observational resources and when it can be catalogued and studied in the normal course of scientific investigation. 3I/Atlas would have rated at approximately level 4 on Loeb's scale, according to the analysis in a paper proposing the scale's framework. Multiple anomalies warranting intensive observation, but not definitive evidence of technological origin. That seems about right as a description of the epistemic situation. There were enough unusual features to justify the extraordinary observational effort that the community brought to bear. The ordinary scientific machine was, in a sense, vindicated by the 3I/Atlas experience. We studied it intensively, we gathered enormous amounts of data, and we arrived at a well-supported natural explanation. That is how the process is supposed to work. What the experience also revealed, though, was how much we still don't know. We don't know where 3I/Atlas came from. We can't trace it to a specific star system. We can't be sure how old it is. We have a relatively good understanding of its chemistry, but the interpretation of that chemistry, what it tells us about the conditions in its home system, requires models and assumptions that are themselves uncertain, and we cannot rule out, in any rigorously scientific sense, that some small fraction of the anomalies Loeb identified were genuinely anomalous in a way that natural comet physics hasn't fully explained yet. The 3 symmetric mini-jets, the unusual nickel ratios, the early activity at Jupiter's distance, these are interesting science problems that don't require alien technology as an explanation, but also haven't been fully resolved by natural explanations. They'll generate papers for years. That is, in the end, what science looks like. Not clean resolution, not a dramatic reveal. Layers of data, competing interpretations, tentative conclusions, and a long tail of follow-on work that extends the conversation indefinitely. The story of 3I/Atlas in 2025 was a story about that process playing out in public, at high speed, with a global audience watching. And the audience's presence changed the story in ways that were both fascinating and instructive. The 40% of social media discourse about 3I/Atlas that invoked alien technology reflected something real about how humans engage with the unknown. We are pattern-seeking creatures. We evolved to find intent in ambiguous signals, to see the predator in the rustling leaves, to hear the warning in the distant thunder. When something appears in the sky that doesn't fit the familiar categories, we reach for the explanation that imputes agency. Because an agent can be reasoned with. An agent has intentions that can be understood. An agent, in the worst case, can be negotiated with or fled from. A random cosmic object cannot. Loeb, whatever his critics say about his methodology, was tapping into something genuine when he argued that we should at least be asking the question. Not because the alien technology hypothesis was likely, but because the alternative, assuming that everything unusual has a natural explanation without rigorously demonstrating that it does, leaves us unprepared for the possibility, however remote, that it doesn't. The history of science includes many examples of phenomena that were assumed to have natural explanations before those explanations were verified, and in most cases the assumptions turned out to be correct. But not always. The universe is under no obligation to deliver only the phenomena our models predict. If something genuinely artificial ever does appear in our solar system, the ability to recognize it will depend on having developed the conceptual tools to look for it, and on having built the observational infrastructure to detect the signatures that distinguish it from the natural background. 3. Atlas forced those conversations into the open. That alone gave it a significance beyond the scientific data it provided. There is a sentence that Loeb kept returning to, in interviews and blog posts and papers, throughout the months of the 3I/Atlas encounter. He phrased it different ways at different times, but the core of it was this: it could come to save us or to destroy us. We'd better be prepared for both possibilities and verify that all interstellar objects are just rocks. Set aside the alien framing for a moment, because the underlying point applies more broadly than the alien technology hypothesis. It applies to the entire enterprise of studying interstellar visitors. The solar system we live in is not a closed system. It has never been a closed system. Interstellar space connects it to every other star system in the galaxy, and objects travel those connections constantly, on timescales of millions and billions of years. For most of human history, we had no way to perceive that traffic. We lived inside our solar system like creatures living inside a house with no windows. We could observe everything in the interior. We could study the furniture and the walls, but we had no way to see what was moving outside. The Atlas telescope, and its successors like Vera Rubin, are the first windows. 3I/Atlas is among the first things we saw when we looked through them, and what we saw was genuinely informative. A comet from another star, ancient and fast, carrying chemical signatures of conditions we cannot otherwise access, telling us something real about the diversity of solar system chemistry across the galaxy. That is valuable. It is scientifically profound. It will shape our understanding of planet formation, of the distribution of volatiles in different stellar environments, of the chemical conditions that either favour or disfavour the emergence of life. But there's another dimension to what those windows show us, and it's the one that Loeb kept pressing on. If interstellar objects pass through our solar system with the regularity that the detection of 3 of them in a single decade suggests, and projections from the Rubin Observatory's expected detection rate suggests that regularity is real, then those objects are a permanent feature of our astronomical environment. They always have been. We just couldn't see them. Some of those objects will be simple comets, carbon and ice, ancient, drifting, scientifically interesting, but posing no special challenges beyond the standard ones of orbital mechanics and observational astronomy. The vast majority will probably fall in this category, but some might be different. Not necessarily in the way Loeb suggests, not necessarily in the alien technology sense, but different in other ways that matter. An interstellar object on a particular trajectory could, in principle, pose a collision risk with Earth or another planet. The probability is vanishingly small for any individual object, but over billions of years and billions of objects, the statistics accumulate. We have impact craters to prove that the solar system has been struck by large bodies throughout its history. The practical point is that we need to be watching, not in a state of alarm, not with the assumption that every fast-moving rock is a threat, but with the systematic attention that a potentially significant environmental category deserves. The current situation is that we have telescope networks, primarily ATLAS, and the Rubin Observatory, that are capable of detecting interstellar objects well before they reach the inner solar system, giving us months of warning and observation, time before any close approach. That's a good starting point. But the institutional response to those detections is not yet formalized. When 3I/ATLAS was discovered, the scientific community's mobilization was rapid and impressive. Dozens of institutions turned their instruments toward it within days. NASA and ESA coordinated spacecraft observations. The Minor Planet Center processed thousands of observations from hundreds of observatories. The result was the most comprehensive study of an interstellar object in history. But much of that coordination was improvised. It happened because scientists are curious and flexible, and because the discovery was exciting enough to generate its own momentum. It was not the result of a pre-existing protocol, a designated coordinating body, or a standard international response framework. Loeb has argued for the creation of such a framework, an international organization specifically tasked with monitoring interstellar objects, developing detection and response protocols, and making coordinated recommendations about how to study and, if necessary, respond to unusual ones. He draws parallels to existing frameworks. The International Atomic Energy Agency for Nuclear Materials, the Intergovernmental Panel on Climate Change for Climate Data, NASA's Planetary Defense Coordination Office for Near-Earth Asteroid Threats. Each of these institutions represents a collective recognition that certain categories of phenomena are important enough to merit systematic international attention rather than improvised national responses. Whether Loeb's specific proposals gain traction or not, the underlying argument has merit. Interstellar objects are a real category of astronomical phenomenon. They will be detected with increasing frequency as survey capabilities improve. Some of them will be unusual. Having agreed criteria, agreed protocols, and agreed institutional responsibilities for studying and responding to them seems like a reasonable precaution. It's also worth noting what 3I/ATLAS demonstrated about the practical cost of taking an unusual interstellar object seriously. The Extraordinary Observational campaign that was mounted in 2025, the Hubble re-observations, the JWST spectroscopy, the Mars Orbiter flyby observations, the Parker Solar Probe perihelion watch, the JUICE observations, the TESS and SPHEREX campaigns, consumed real resources. Telescope time is finite and valuable. Spacecraft operations require planning and budget. Every observation of 3I/ATLAS displaced some other observation of something else. The scientific return was worth it. The data gathered from 3I/ATLAS will inform research for years. But if the detection rate of interstellar objects increases to 1 per month, as Rubin projections suggest is possible, the question of how much observational resource to devote to each one becomes a genuine allocation problem. Having criteria, having something like the Loeb scale or a successor framework, would help make those decisions systematically rather than reactively. The scientific community is, slowly, working toward this. There are papers being written, conferences being organised, research groups focused specifically on the science and policy dimensions of interstellar object encounters. The 3I/ATLAS experience accelerated that work in a way that Oumuamua and Borisov, despite their own scientific significance, didn't quite manage. The combination of 3I/ATLAS's unusual properties, the public debate generated by Loeb's papers, and the extraordinary observational record built up during the encounter has made it a reference case, the object that defines what a serious response to an unusual interstellar visitor looks like, and what a serious response to the debate about such visitors looks like. There's a broader scientific payoff waiting in the future as well. The Rubin Observatory will find interstellar objects at high rates. Some of them will be better studied than 3I/ATLAS. detected earlier, approach more closely, perhaps even intercepted by a dedicated mission. The European Space Agency has already begun preliminary planning for what a fast response interstellar object mission might look like. A spacecraft capable of launching within days of an interstellar object discovery and catching up with it before it leaves the inner solar system. Such a mission would transform what we can learn from these visitors. Instead of studying a comet from hundreds of millions of miles away, we could send a spacecraft to fly alongside it, to image its surface directly, to measure its magnetic field, its density, its internal structure through radar, to sample the gas of its coma directly with a mass spectrometer, to look for whatever is there, without the interpretive layers imposed by remote observation. If 3I/Atlas had been intercepted by such a mission, if we had been able to fly a spacecraft within a few thousand kilometers of its nucleus, many of the questions that remain open about its nature would be answerable. The nuclear size would be directly measured, not inferred. The jet structures would be imaged directly, not reconstructed from the blurred evidence of ground-based photographs. The surface composition, the internal density, the presence or absence of any features inconsistent with natural cometry structure, all of it would be accessible. We didn't have that capability in 2025. We weren't ready. The 3-week window between discovery and the comet's closest approach to the inner solar system was not enough time to launch and navigate any existing spacecraft to an intercept trajectory, but work is underway to change that. ESA's Fast Response Mission concept, sometimes called the Comet Interceptor Mission, in a broader sense, is part of that work. The key challenges are launch readiness, having a spacecraft either already in orbit or ready for rapid launch, and delta V, the change in velocity needed to match trajectories with a fast-moving hyperbolic object. 3I/Atlas was moving at 58 kilometers per second. No chemical rocket we have could match that directly from Earth, but a spacecraft already in space, on a carefully chosen orbit, might be able to intercept such an object with a relatively modest velocity adjustment if the geometry is favourable. The next interstellar visitor might give us a better opportunity. It might arrive on a trajectory that gives more warning time. It might move more slowly. It might pass through a part of the solar system where our planned missions happen to be positioned, or it might not. It might arrive like 3I/Atlas, suddenly fast, giving us months rather than years. Either way, we need to be ready. And 3I/Atlas has, in its passage, given us both the scientific context and the institutional motivation to start getting ready more seriously. There's a specific kind of feeling that comes from watching something leave, not the dramatic departure of a spaceship launching from a pad, fire and smoke and the sound rolling across the landscape, not even the slow fade of a comet at the edge of visibility, where you know it's still there and you could find it with a large enough instrument. The kind of leaving I mean is quieter than that, the kind where the thing that's gone was never yours to keep, where the absence is not loss so much as the natural completion of a passing. 3I/Atlas passed through our solar system. It is now leaving. By the time you hear this, it has already travelled further from the sun than it was on the day we found it. It is cooling. The coma that made it visible is thinning, fading, the volatiles sublimating at an ever slower rate as solar heat diminishes across the increasing distance. In a few months it will be, to all practical purposes, invisible again. A point of light, then nothing detectable at all, then truly gone, back into the interstellar medium from which it came, back into the dark spaces between the stars. It will travel outbound at 58 kilometers per second, the speed it arrived with until the sun's gravity has done all the slowing it can do. Then it will maintain that speed more or less indefinitely, a piece of another solar system moving through the Milky Way, until some gravitational encounter adds or subtracts velocity, until something changes its trajectory, until, possibly in billions of years, it falls into some other star system's gravity well and begins the process of being observed and wondered about all over again. In early 2026, as it moves into the region of Jupiter's orbit. NASA's Juno spacecraft will make one more set of observations. Juno is designed to study Jupiter's magnetic field and interior structure, but its wide-angle camera can capture images of other objects in the vicinity. The 3I/Atlas observations from Juno will be among the last good measurements we get from a nearby spacecraft. After Jupiter, there's nothing. No spacecraft in our outer solar system is positioned to observe 3I/Atlas further. The Voyager probes are in interstellar space, but cannot be pointed and do not carry cameras useful for this purpose. New Horizons, which visited Pluto in 2015 and is now also in the outer solar system, is focused on other targets and is not in a geometry to observe 3I/Atlas's departure. Humanity will watch it go until it becomes invisible, and then it will go. What remains is the data. Thousands of observations from hundreds of observatories on Earth and in space, spanning a 6-month window from first detection to last useful measurement. Chemical analyses from Webb's spectrographs constraining the ratio of CO2 to water and identifying a dozen molecules in the coma. Size constraints from Hubble, placing the nucleus somewhere between 320 meters and 5.6 kilometers, with the most physically consistent estimates clustering around half a kilometer to 3/4. Speed and trajectory data from the network of astrometric observatories that tracked it across the sky, constraining its orbital parameters to extraordinary precision. Images from Gemini, from Subaru, from amateur observers around the world, capturing the evolution of its coma and tail as it heated and then cooled. Polarimetric measurements, infrared maps, X-ray observations, the detailed chemical record of a body from another star. That data will be analysed and reanalysed for years. Papers examining specific aspects of 3I/Atlas's properties will be published throughout 2026 and beyond. Each one will add a small piece to the mosaic. Some will refine existing conclusions, some will raise new questions. Collectively, they will build the most detailed picture ever assembled of the chemistry and physics of an interstellar comet. It won't be the last such picture. The Vera C. Rubin Observatory is scanning the sky. The algorithms for detecting interstellar objects are being refined. The detection rate is projected to increase substantially as both the telescope's capabilities and the analytical tools improve. The next interstellar visitor may already be in images taken this year, waiting to be found in the archive, or it may arrive next month or next year, announced by the same kind of alert that brought 3I/Atlas to our attention on that July night in Chile. And when it arrives, we will know a little more about how to study it. Because 3I/Atlas taught us something about the practical reality of observing an interstellar object. The timeline is compressed, the data comes fast, the interpretation is contested, and the most important thing is to have as many eyes on the object as possible for as long as possible. We also know, because of 3I/Atlas, that the scientific community can mobilize quickly when the stakes are clear. The network of observatories, the spacecraft assets, the community of researchers willing to drop other priorities and focus on a new discovery. All of that existed before 3I/Atlas arrived, and 3I/Atlas activated it within days of discovery. That capability is real, and it's valuable, and the experience of using it has improved it. The debate around Loeb's hypothesis, the public argument about whether 3I/Atlas could have been alien technology, will fade, as most scientific controversies eventually do, into a reference point in the history of the field. Future papers about interstellar objects will cite 3I/Atlas. Future textbooks on solar system science will include a section on interstellar visitors and use it as the primary example. Future astronomers will know about it the way current astronomers know about Halley's Comet or the Shoemaker-Levy impact on Jupiter, not necessarily because they watched it in real time, but because it was significant enough to persist in the scientific record. The specific claims Loeb made will be evaluated in light of the full dataset. Some will be vindicated in the narrow sense that the anomalies he identified were real anomalies, things that didn't fit the standard model and required updated models to explain. Some will be superseded by natural explanations that become clear only after full analysis. None of them, based on all available evidence as of early 2026, have provided definitive evidence of artificial origin. But here is the thing that doesn't go away, the thing that sits quietly at the centre of the whole story, regardless of how the specific debates resolve. 3I/Atlas came from another star. Something formed it in another solar system, under conditions we can partially reconstruct but not fully know. It spent an unimaginable length of time, possibly longer than the Earth has existed, in the cold and dark between the stars. It entered our solar system, encountered the gravity of Mars and Venus and Jupiter, rounded our sun at a speed no human has ever travelled, came within 170 million miles of the planet, where all of human civilization has unfolded and then left. We watched it, we measured it, we argued about it. We wrote papers about it and posted images of it and stayed up late pointing telescopes at it from rooftops and mountaintops in orbit. We added it to the catalogue of our knowledge, this small and ancient piece of somewhere else. And in a universe 13.8 billion years old, in a galaxy containing hundreds of billions of stars, that catalogue is just beginning. The sky is full of travellers. Some of them are passing through our solar system right now, too faint and small to detect with current instruments. Some of them passed through before any eye existed on Earth to see them. Some of them will pass through billions of years from now, long after humanity is whatever it will become or whatever will have succeeded it. They come from everywhere. They carry the chemistry of other worlds, the fingerprint of other suns, the evidence of processes we are only beginning to understand. They are the closest thing we have to a message from the rest of the universe, not a deliberate message, not a signal crafted by an intelligence trying to reach us, just the physical reality of a cosmos in which materials travel, and the boundaries of solar systems are not barriers, but merely local concentrations in an infinite sea. 3I/Atlas is gone. The doubt remains, the questions remain. The sky above us remains full of motion we're only now learning to see. There will be another one. There will be many more, and when they arrive we'll be watching. This has been the complete story of 3I/Atlas, the third interstellar object ever confirmed in our solar system, discovered July 1st, 2025, observed by more telescopes and spacecraft than any interstellar object in history, and now outbound into the dark between the stars, never to return. If you found yourself drawn into this story, consider that the next chapter is already being written somewhere above us, in the survey data flowing off the Vera C. Rubin Observatory sensors every night, in the algorithms processing thousands of asteroid candidates for the unusual ones, in the papers being written by researchers who spent 2025 pointing every available instrument at a smudge of light in a Chilean sky survey. The universe is under no obligation to stop being interesting. It hasn't yet. Rest well. The sky above you is full of travellers. It's worth pausing here to understand why Oumuamua, the first interstellar object, matters so much to the 3I/Atlas story. Not because it proves anything about 3I/Atlas, but because it established the pattern of the debate, the specific shape of the argument between Loeb and his critics that played out again, amplified in the 2025. Oumuamua was discovered in October 2017 by the Pan-STARRS telescope at the Haleakala Observatory in Hawaii. It was spotted while it was already departing the inner solar system, which meant the observation window was even shorter than the one we had for 3I/Atlas. Astronomers had weeks, not months, to study it before it faded beyond detection. What they found was baffling. Oumuamua was elongated to a degree not seen in any solar system object. Estimates at the time placed its length to width ratio at somewhere between 5:1 and 10:1, like a cigar or a needle. It tumbled slowly, reflecting sunlight in a distinctive pattern, and when it reached the point in its trajectory where the sun's gravitational pull should have fully dominated its motion, it continued to accelerate slightly more than pure gravity predicted. That extra push, what astronomers call non-gravitational acceleration, is expected in comets, where the force of outgassing produces a small but measurable rocket effect. But Oumuamua showed no detectable outgassing, no coma, no tail, no trace of gas being expelled. A comet that behaved like a comet in terms of its trajectory, but showed no signs of being a comet in terms of its visible appearance. The natural explanations for the non-gravitational acceleration were multiple and varied. Pressure from solar radiation on an unusually flat object, flat enough that the pressure would be significant even without any outgassing. Outgassing of hydrogen, which is invisible to standard telescopes. Fragmentation releasing gas in a way that didn't produce an observable coma. All of these explanations were physically possible. None were fully satisfying. Loeb's light sail paper proposed an alternative. If Oumuamua were an extremely thin, flat object made of a material with low enough density, solar radiation pressure alone, without any mechanism beyond the physics of photons bouncing off a reflective surface, could account for the observed acceleration. A light sail, not necessarily a functioning spacecraft carrying a crew or sophisticated instruments, possibly a derelict, a piece of technology cast adrift, drifting through the galaxy long after whatever civilization built it had moved on or died. The paper was published in the astrophysical journal Letters. It underwent peer review before publication. It was not the work of someone operating outside the scientific process, and it generated enormous controversy, not primarily because it was wrong. We still don't know definitively what Oumuamua was, but because of what many scientists perceived as a methodological problem. The light sail hypothesis, like any hypothesis that invokes an unknown technology as the explanation for an anomaly, is almost impossible to disprove directly. You can't falsify it in the usual sense by collecting more data, because any data consistent with the natural explanations is also consistent with a sufficiently advanced technology that mimics natural behavior. The hypothesis is unfalsifiable in the near term, which means it doesn't fully meet the standards of predictive, testable science. Loeb's response to this objection was that unfalsifiability is not the same as being wrong. Many hypotheses that later turned out to be correct were, at the time of their proposal, difficult or impossible to test with available technology. What matters is not whether you can currently test a hypothesis, but whether it is physically plausible and consistent with the available data. And the light sail hypothesis for Oumuamua was, he argued, physically plausible, thin but not impossibly thin, consistent with the measured acceleration, not contradicted by the absence of a detectable coma, because a light sail doesn't need to outgas. The debate went nowhere definitive, because the data ran out before the argument did. Oumuamua left the inner solar system. The opportunity to collect more data passed. The controversy remains unsettled to this day, which is itself an unusual status for a scientific debate. Most of them eventually resolve one way or another as evidence accumulates. When 3I/Atlas arrived in 2025, Loeb had both the experience of Oumuamua and a much larger public platform. He had written a best-selling book. He had founded a research project. He had given hundreds of interviews. He had refined the framework of his argument, developed the vocabulary for it, and built a network of colleagues and collaborators willing to engage with the alien technology hypothesis as a serious scientific proposition rather than a fringe curiosity. And 3I/Atlas gave him new material. Unlike Oumuamua, which had been small and inert and had left almost nothing to observe, 3I/Atlas was large, active, and present in the inner solar system for months. There was far more data, and far more unusual features, the trajectory, the chemistry, the jet structures, to which the alien technology framing could be applied. The critics who had challenged Loeb after Oumuamua were still there, making the same methodological arguments, but the platform on which the debate played out was orders of magnitude larger. Social media in 2025 was a different environment from social media in 2017. Science communication had changed. The viral dynamics of the alien narrative were more powerful, and 3I/Atlas, unlike Oumuamua, was something that amateur astronomers could actually see with modest equipment, which gave it a visual and emotional immediacy that made the public engagement far more intense. The result was a debate that was simultaneously more scientifically rich, more data, more telescopes, more papers, more precise measures.